The Reynolds transport theorem or RTT, which plays a critical role in fluid dynamics. There are two ways to analyze fluid system as illustrated within the Deodonis spray explained. First, we have the system approach. Here we follow the fluid as it moves as deforms, keeping the system boundaries fixed to that no mesh crosses them. This is useful for tracking individual fluid particles. Second, we have the control value approach. Instead of tracking particles, we focus on a fixed interior volume within the can, allowing mesh to cross the boundaries. RTT bridge these two methods by expressing the relationship between the time rate of change of an extensive property for the system and for control value. This connection helps us understand and analyze dynamic system more effectively, combining both perspectives. In summary, RTT provides the necessary framework to link the physical understanding of fluid in motion with practical engineering analysis. The Reynolds transport theorem, which connects the time rate of change of a property B within a system to the control volume approach. The equation shown expresses that the rate of change of B in the system, dB system over dt, equals the rate of change of B within the control volume, dB control volume over dt, plus the net flux of B across the control surface represented by B and B out. In the diagram, the control volume remains fixed, while the system moves with the flow. At time, the system and control volume coincide, but at t plus delta t, the system overlaps partially with the control volume and extends outside it. The flux term account for the inflow and outflow of property B across these boundaries during delta t. The theorem is fundamental for analyze fluid flow and other engineering systems because it bridges the system-based and control volume perspectives, make it easier to apply conservation law like mass, momentum, and energy. This slide builds on Reynolds transport theorem and demonstrates its derivation step by step. It begins by defining as any extensive property such as mass, energy, or momentum, and its corresponding intensive property as per unit mass. At times, the system and control volume coincide. At times, the system and control volume coincide, so at the system is split into portion inside and outside the control volume by subtracting and dividing by and then taking the limit as we derive the general equation. Taking the limit as delta t equals to 0 and using the definition of derivative, we get dB system over dt equals to dB control volume over dt minus B in plus B out. Or we can use dB system over dt equals to dB control volume over dt minus Bp Va plus Bp Va2. Since we can use B1 plus delta R equals to B1 M1 plus delta R equals to B1 P1 V1 plus delta R equals to B1 P1 V1 delta T A1. Or we can use the B in equals to B1 equals to B1 plus delta R over delta T equals to BP V delta T A1 over delta R equals to B1 P1 V1 A1. These account for changes inside the control volume and the flux of entering or leaving the control surface. Substituting specific expression for inflow and outflow terms, and we relate these fluxes to the properties density, velocity, and areas at the respective inlet and outlet. The detailed approach ensures conservation principles are accurately applied across the control volumes. This slide focuses on the flux of a property B across the control surface and its connection to the Reynolds transport theorem RTT. The equation for B out minus B in is expressed as an integral over the control surface. Integrate CS PB darab V darab dengan N dA, where V darab N represent the component of velocity normal to the surface. The diagram clarifies how inflow and outflow are determined by the angle theta between the velocity vector V and the outward normal N. For 0 is less than 90 degree, cos cos theta is bigger than 0, indicating outflow, while for 0 less than 90 degree, cos theta is less than 0, indicating inflow. The integral of Bp dV over the control volume gives the total amount of B in the volume, while RTT relates the time derivative of B system to change inside the control volume and across the surface. The alternate RTT formulation at separate time variation of PB and the flux terms, emphasizing their roles in system behavior. This slide highlights the importance of evolution flux integrals accurately for conservation law like mass, momentum, or energy. This slide explains the application of the Reynolds transfer theorem RTT to a control value moving at a constant velocity. RTT is a fundamental principle in fluid mechanics that relates the rate of changes of property in the system to its behavior within a control value. First, we observe relative velocity, which is the difference between the absolute velocity of the fluid V and the velocity of the control surface V CS. This relative velocity determines how the fluid interact between the moving control value. The top equation describes RTT for non-fixed control volumes and for steady flow. For steady flow, the change in the system property dB system over dt. Simplify the flux across the control surface given by integrate CS P darab VR darab dengan N and D. In the diagram, the absolute reference frame shows a stationary observer measuring and velocity of the jet and car. In contrast, the relative reference frame accounts for the car's motion, resulting in a relative velocity in the fluid V jet minus V car. Understanding relative velocity is crucial for analyzing moving control values such as vehicle or jet in real-world applications.